This is the Formula SAE Suspension Team. My name's Mackenzie, and my teammates are Seth, Steven, Harrison, and Garrett. Today we'll be talking about our capstone project.
Job was to find the center of gravity and total vehicle weight estimates for the new design. To do this, I used the former vehicle that we have right here. I split this vehicle into as many individual components as possible. Each of those components I weighed and found the relative location of the center of gravity relative to the center of the rear axle of the car. Once I had all these values, I met with individual members who were responsible for the new designs and worked with them on what design changes did they expect to make. For example, if we anticipated changing designs of the uprights, would this new design be heavier or lighter than the current one, and would its location change massively in the XYZ direction for the center of gravity? Once I had talked to all the members, I created error bounds for the weight and center of gravity location for each component. Adding all of these together created what we expected to be the total weight maximum and minimum, as well as the range of where the center of gravity might lie within the vehicle. And these values were used to design the other suspension system components.
In the design process of the Formula vehicle, we needed to determine the steering ratio. After some research, we found some equations to get an approximation for the steering ratio. However, the approximation was only good as long as the angularity in the system was minimal and that the tie rod was nearly perpendicular to the steering arm in the top and front views. However, our design does not fit this. With this in mind, we determined that an equation would have to be derived for our specific steering setup. We used a form of the Pythagorean theorem to get an equation for the steering rack travel as a function of the wheel angle. We were able to plot the rack travel versus the wheel angle. We then simulated a similar joint motion and captured data points in 10-degree intervals. Overlaying the two data sets allowed us to validate that our equation was correct. We then plotted the steering wheel angle versus the wheel angle. A first-order linear approximation was calculated to determine the steering ratio for relevant steering wheel angles.
The rear upright is a crucial component of the suspension system that needed a redesign for 2022. The 3 improvement areas we identified were weight reduction, rim clearance, and updated tie rod location. This is the previous year's upright, and each of the 3 problem areas is very evident on this design. The design process for the rear upright yielded 3 iterations. Version 1 is building up the concept from the previous year, while version 2 is a complete redesign with a minimal philosophy. The third and final version merges the best of the two by minimizing the material usage while maintaining the necessary structural rigidity. This upright has been placed into wheel assembly, seen on the left, and it does not interfere with the rim. This upright improves on each of the 3 identified design improvement areas.
Taking a look at the brakes for the vehicle, we were asked by our client to see if a one-rotor brake system would work to meet brake standards of the Formula FSA rules and regulations with the current vehicle design. A one-rotor brake system would be a cost savings and reduce some weight on the vehicle. After running through some intensive calculations, it was determined that a one-rotor brake system would not work with the current vehicle, so we then took to optimizing the 2-rotor brake system that the vehicle already had. Replacing the current rotors with a large front rotor and small back rotor along with increasing the brake pad coefficient of friction appeared to be the best solution. We investigated several compounds and determined that the Wilwood BP40 high-temperature racing brake pads would be sufficient to meet the braking criteria of the Formula FSA rules and regulations, as well as giving us optimal braking with the current vehicle design.
This is the current CAD design. This shows a relationship between the suspension and the frame. For example, the mounting points for the control arms have to be mounted at nodes in the frame, so we use this CAD to create the proper relationship between the suspension and the frame. The shock and rocker locations for the front and the rear were a needed design improvement for the suspension system. Due to time limitations, the previous team was not able to create a proper shock and rocker configuration, so this was a big need for improvement for the suspension design. The front shock and rocker locations were created using the current CAD design. This configuration has the pushrod mounting point, rocker, shock, and the desired mounting frame member all in plane. In addition, this design has a perfect node for the rocker mount as shown in the figure. This proves to be an ideal design, and this design is a simpler design than the previous year, but creates a better distribution of forces across the desired mounting frame member. The rear configuration had some problems due to there not being a node in the rear for the rocker mount and the desired mounting frame member for the shock being out of plane. We deliberated heavily with the frame team to make the proper adjustments to achieve a feasible configuration while conforming to the standards in the Formula SAE rules. The finalized design has been placed in a position that is best for the suspension system given the limited space in the rear. Through deliberation, the frame team has adjusted the rear frame accordingly to create a feasible mounting member for the shocks and feasible nodes for the rocker mounts as shown in the figure. This design proves to better meet the design standards for the Formula SAE rules, creates an improved distribution of forces, and creates more spacing for other FSAE teams' components. Overall, we have made great strides in the improvement of the FSAE suspension. We would like to give a special thanks to our mentor, Dr. Mativo. Thank you.